Hello everyone, we are continuing with our Introduction to Photonics video series with lecture number 2. Lecture number 2 deals with the wave behavior of light. We've seen in the first lecture that light represents an electromagnetic wave or a form of electromagnetic energy that has both wave and particle properties. In this lecture, we are going one step further and analyzing some of the specific phenomena that can be explained only if you're looking at the light as a wave. So we are going to be analyzing a few phenomena related to the light, specifically reflection, refraction, and then also we are going to establish a few laws, specifically law of reflection and so-called Snell's law of refraction that will be used to quantify the behavior of light as a wave in the case of behavior when the light hits another medium or propagates from one medium into the other medium, etc. And finally, at the end, we're also going to talk a little bit about the diffraction and interference, which are also the phenomena that pertain to light wave behavior. With this slide, we're introducing another quantity that is related to the wave behavior, so-called phase. As already mentioned, waves exhibit a certain wave behavior that can be represented by the sinusoidal curve as shown on the plot on this slide, and that wavy behavior or that sinusoidal behavior is both in a time domain and in a space domain. In other words, we have a vibration both in time and space. Another way to represent the wave behavior is in terms of so-called phase, where on the x-axis, instead of units of length or units of time, we are putting the units of angles, and we see that the total period is equal to can be correlated to the phase of 360 degrees. So by doing this type of correlation, we can remove the dependence of the x-axis from time and space and look at everything in terms of angles, which greatly simplifies the whole mathematical analysis of these types of behaviors that can be described by sinusoidal curves. So we can define the phase of a wave as the angular displacement of a specific point on the sinusoidal curve from the last positive zero crossing of the wave, where a positive zero crossing occurs at those zero displacement points where the new displacement is about to become positive. All these are the properties of sinusoidal functions that can further be elaborated through the concepts of trigonometry that's going to go beyond this class. Now, why is the phase as a quantity important for us? If you compare the two waves that you are seeing on this slide, you can see that both of these waves exhibit a very similar pattern, in the sense that their phase is that their wavelength or frequency are the same. In other words, the distance between the two peaks on these two curves is equal. In other words, since we are dealing here with a distance along the x-axis, we are dealing with the wavelength. In other words, the wavelength of the wave 1 and the wavelength of the wave 2 are the same. However, you can also observe that the two peaks of the two waves are not perfectly synchronized. In other words, they are not occurring at the same location. So if you look at the peak of the wave 1, you can see that the peak of the wave 1 is at a different location than the peak of the wave 2. In other words, we are talking about so-called phase difference that in this case here is equal to 90 degrees. That is going to result in a certain interference behavior between these two waves if they are occurring in the same space. We would use the term coherent to describe multiple light waves that are all in phase or in step with one another. So the coherent behavior of multiple light waves is shown on a plot on this slide, and as you can see, the peaks of all these different 6 waves are basically occurring at the same location if we are dealing with sinusoidal curves that are represented as a function of a space or a distance. So coherent light is made up of waves that each have the same wavelength and that are all in phase. When added together, these coherent waves would produce an overall wave of a much greater amplitude with very high peaks and lower valleys. So in other words, they are perfectly synchronized. It's almost like we are creating a perfect storm that consists of all these different waves. We'll see that coherent light is actually a behavior of light that's coming out of the lasers, and it's directly related to the power of a light. In other words, if you want to establish a very high power of a specific light source, you would want to create a coherent type of a light, which in this case, as mentioned, is going to be most probably a laser. As opposed to the coherent light, we also may have an incoherent light. So in the case of incoherent waves, these waves, they do not possess identical phase angles along the vertical line. We can see that in this example, we are having 4 waves that have different wavelengths or frequencies, and if these waves are added together, they will produce an overall wave of smaller displacements. So we may have a different types of interference here that can be either constructive or destructive based on how these waves are lined up. So in this case, again, we are dealing about an incoherent light that is a representation of light that's coming from different types of non-laser sources like arc lamps, incandescent bulbs, and also the light that's coming from the sun. So in general, incoherent light is not having a strong power, or it's having a significantly less power than the coherent light that's produced from laser sources. So to summarize, the light based on its phase may be either coherent, where the waves are synchronized from the phase perspective, and in order to have a coherent light, multiple waves would have to have the same wavelength. As opposed to the coherent light, we may also have an incoherent light where the waves are not phase synchronized, and most of the time they also would have a different wavelengths. Incoherent light in general does not have as strong effect as the coherent light. In other words, the power of the coherent light is much higher than the power that can be achieved by the incoherent light. An important property of a wave behavior is an ability to reflect from a surface between the two media. So here we are dealing with an incident light ray that is hitting a certain surface between the two media, and what's going to happen when the light hits that medium is explained through the concept of so-called reflection. So we are going to have a reflection of light. The question is, in what direction this light is going to be reflected. It can be quantified through a so-called law of reflection. So how we are establishing the law of reflection, we are looking at the point of reflection of the light. At that point of reflection, we are establishing the axis that is perpendicular to the surface between the two media. So we have one medium from light, from which the light originates, that's represented here as an incident ray, and then down below this surface is a different medium. So when the light hits this surface between the media on the above and the media below, it is going to reflect. At that point of contact or point of reflection, we are going to establish the axis or a norm or a line that's perpendicular to the surface between the two media, And then we are going to be measuring two angles. One angle is so-called incident angle, represented here as angle A. And then we're also going to have a reflected angle, which is basically the angle that the reflected light ray is going to establish relative to the axis, to the normal axis. That is going to be the angle B. It turns out that according to the law of reflection, these two angles are equal. In other words, the incident angle A is equal to the incident angle B. So once more, the law of reflection states that the incident angle and the reflected angle are equal to each other, where incident angle is established by the incident light ray and the axis normal to the surface of the reflection, while the reflected angle is established as an angle between the reflected light ray and normal axis. It's also important to mention that incident light ray, reflected light ray, and normal, or the axis that's perpendicular to the surface of reflection, are always positioned, lie in the same plane surface. So this plane here that you can see, that's being established by the incident light ray and the reflected light ray and the normal axis, is the plane in which all these three light rays are positioned. Another important phenomenon that's related to the wave behavior of light is so-called refraction, or popularly known also as a bending of light. So it turns out that light always propagates along the straight lines as long as it propagates within the same media. If the light is going to move from one medium into the other medium, a phenomenon that's known as a refraction or bending is going to occur, where the direction of the propagation of light is going to change. So here we are dealing with two media. Medium number 1, that's characterized by the index of refraction N1, that's positioned above this interface, and then we also have the medium number 2, that's characterized by the index of refraction N2, that's positioned below the interface. And we can see that the light is incident from the medium 1. It's going to hit the surface between the two media, and then to a certain extent it's going to get reflected, which is what's been already analyzed on the previous slide. And then to a certain extent it's going to get bent or refracted into the second medium. So we have incident light ray, we have a reflected light ray, and we have a refracted light ray. For the purpose of the refraction or bending, what we are interested here are the incident light ray and the refracted light ray. So we want to quantify how much is light gonna get bent or gonna get refracted relative to the incident light ray. Is it going to get refracted towards the normal, towards the axis, or it's going to get refracted away from the axis? So we want to establish direction of propagation of the refracted light. There's a specific law known as Snell's law of refraction that quantifies this behavior. The formula that represents the Snell's law is given here in the top right hand corner. N1 times sine function of angle theta 1 is equal to N2 times sine function of angle theta 2. So let's try to decipher what is this in this equation. What you see on the left hand side of the equation is everything what pertains to the first medium or the medium from which the light originates, and what's on the right hand side is everything what pertains to the second medium, or the medium into which the light is going to get refracted. N1 represents the index of refraction of the incident medium, while N2 represents the index of refraction of the second medium. The angles theta 1 and theta 2 are incident angle and refracted angle. How we are establishing these two angles? We are going to first establish the line that's perpendicular to the surface between the two media. This is going to be this dotted line, and then the angle that incident light ray is going to establish with that axis is equal to theta 1, while the angle that the refracted light ray is going to establish with that axis is represented by theta 2. So these two angles, theta 1 and theta 2, that appear in the formula for Snell's law of refraction are the incident angle and the refracted angle. And we can also see that based on optical density of the two media, optical density that's been characterized by the two indexes of refraction N1 and N2, so the optical density is going to have an effect on how much light is going to bend into the second medium. So for different values of N2 and N1, we're going to have different amounts of refraction, and this is going to be analyzed in a greater detail in the slides and lectures that follow. Here we have a table that presents some of the indexes of refraction of the most popular media used in the field of photonics. So for the case of air, index of refraction is very close to 1. And then we have a diamond with an index of refraction 2.42, gallium arsenide used in semiconductor technologies, and then we have a glass, zircon, etc. So all these different media that you can see here have different indexes of refraction. So as already explained, there is a physical meaning of this number. We said that index of refraction represents the factor by how much speed of light is reduced in a specific medium relative to the speed of light in air. And then also these indexes of refraction would determine so-called optical density of a specific medium, and also are going to affect by how much the light is going to bend or refracted if that medium is the medium at which interface the refraction takes place. The next phenomenon that characterizes the wave behavior of light is so-called interference or so-called diffraction. So it turns out that when we have light waves, multiple light waves of the same wavelength that are in phase coming from two different sources and are directed onto a screen, they could be made to overlap and interfere with one another. As briefly shown or presented on this slide, we can see two light waves that are hitting the screen, and we can see that at certain locations these two light waves are going to interfere in the sense that they will be adding up, creating the bright lines, while on the other locations on the screen they will be canceling each other out, resulting in a dark line on the screen. So this is so-called interference or diffraction of light that is going to be analyzed further on the slides that follow. So once more, to emphasize the concept that's been introduced on the previous slide, we're dealing with the two light waves that are emanating from slits S1 and S2. So we are dealing with a filter here that consists of two slits through which we are passing the light. So these two slits act as two separate sources of light, creating two separate waves, and then these two waves will be interfering with one another. So the light that's moving outwardly from S1 and S2 will overlap and reinforce each other along the lines with solid dots. So if you're looking at the solid dots, those would be the points where the peak of one wave and the peak of the other wave are overlapping, while we also have locations with these unfilled dots where we have overlap of the positive peak of one wave and the negative peak of the other wave, where those two positive and negative peaks will be canceling each other out. So if you put the screen in the back, you'll see that you're going to have an alternate position of the regions of bright and dark lines that would make up so-called interference fringes that are also shown here on a right-hand side. So at the locations where you have so-called constructive interference, where the positive peak of one wave and positive peak of the other wave overlap, those will be the locations where you have a cumulative effect that would result in a bright line, while you're also going to have dark regions that are shown darkest at the centers, where there is an overlap between the positive peak of one wave and the negative peak of the other wave. In other words, these two peaks, positive and negative, will be canceling each other out, resulting in a dark region. that dark region is gonna fade out gradually into the white regions, because between the maximum dark and the maximum bright region we're gonna have limited interference between the two waves. In general, when the light interacts with small openings or sharp boundaries that are of a size of that's comparable to the wavelength of the light, we are gonna have the occurrence of the interference. So interference of light waves would basically produce so-called diffraction patterns. Here we have a few examples of diffraction patterns. Diffraction of a circular nature that results from a pinhole diffraction. We may have single slit diffraction, or diffraction created through the straight edge. So if the light hits the edge that's very sharp, it's going to create also a type of a diffraction. So all in all, the diffraction is another phenomenon that relates to the wave behavior of light, and it's specific to the interaction of light with the small dimensions such as the openings, sharp boundaries or edges, etc. On a few slides that follow, we are going to go step by step to explain the diffraction. Diffraction is I would say a little bit more complex phenomenon that's a little more difficult to be understood than bending of light and reflection. So we want to kind of focus a little bit on the diffraction and analyze it step by step. So what we see here is a small gap or a slit in a filter. At that point, where that location where the slit is positioned, we are going to imagine that there is a light source that creates the wave. And here we see specifically one of the light rays that's propagating along the horizontal axis. It has a wave behavior. In other words, the distance between the two peaks is equal to 400 nanometers, or we are dealing with the blue light. If this light source this light ray is to be simplified, instead of having a sinusoidal curve, we are going to establish the simplification where the peaks, positive peaks of the in this wavy behavior are represented by the dark blue dots, while negative peaks are represented by the light blue dots, and finally the positions at which the sinusoidal curve crosses zero are represented by the unfilled dots. This can be established in different directions of propagation, as can be seen on this slide. And then if we connect a specific type of dots along the same crest, we are going to establish so-called wave fronts. Here the wave front of a positive peak are represented as full lines, and the peaks of the lines of negative peaks or negative wave fronts are represented by the dotted lines. Now we can further simplify our model to present the wave fronts of our light wave, and then even further go one step further and just look at the positive wave fronts. Now let's imagine having two slits with two light sources. We can see that these two light sources are going to create two waves that are represented by their corresponding wave fronts, and we can see that here there are certain locations where the crest of one wave overlaps with the crest of the other wave. So we can identify those spots as the spots where we are going to have so-called constructive interference, where we're going to have a maximum cumulative effects, where the positive peak of one wave and positive peak of the other wave will add up. And if you put the screen those at specific location, those points of constructive interference are going to result in lines or dots of very strong blue light that are positioned at a certain distance. We can do something similar with the red light. It's just that in the case of red light, we have to take into account that the wavelength of light is going to be larger. So we're moving from 400 nanometers to 700 nanometers if we switch from the blue to the red light. And we can also establish similar model for the red light as we established for the blue light. There's going to be certain differences that are the result of the fact that the wavelength of the two waves is different. Shorter wavelength for the blue light would result in blue spots being closer to one another, as opposed to the red spots, red diffraction spots that are positioned further apart due to the larger wavelength of a red light. If you are shooting the white light from these two slits, the white light consists of all the colors. So different colors, different wavelengths will be acting in a different way, in the sense that the position of dots of a specific color is going to be different. So in the case of a white light, what we are going to see is the diffractive behavior, where all colors will be shown at different locations. In other words, we are going to break down the white light into different colors, where the dots of different color will be located at different locations. So that's how we can analyze the behavior of light through specific types of so-called diffraction gratings that you're going to do in a hands-on part of the course. There are certain equations that can be applied to quantify the position of the dots. So if you want to measure the distance between the dots, from the center dot to the first dots on the either left or right side of the center dot, we can use certain approximations based on a trigonometry to come up with the formulas that are shown on this slide. Without going further into derivations of these equations, we can see that the position of the first dot is going to depend on the wavelength of light, distance between the diffraction grating and the screen, and finally the distance between the two openings in the diffraction grating. So the formula that's shown all the way on the bottom is basically a representation of the position y of the dot as a function of lambda, or wavelength, capital D, or distance between the screen and the diffraction grating, and finally small d, which represents the distance between the two slits in diffraction grating. Small letter m is an integer that basically gives us the flexibility to establish or calculate the position of the second, third, and other subsequent dots in the diffraction pattern. So for the first dot, the bright line that is first next to the central line, we're going to take m equal to 1. If we're looking for the second dot or second line, bright line in a diffraction pattern, then we're going to take m equal to 2, etc. Another important property of a wave behavior of light is so-called polarization. When we talk about the polarization, we are talking about the orientation or direction of vibration of the electric field as the wave propagates through space. We can have so-called unpolarized light, we can have a horizontally or vertically polarized light that are in general summarized as a linearly polarized light. So what we are basically trying to analyze here is how does the light vibrate or oscillate in time. In other words, we are trying to establish the planes of a vibration of electric field in an electromagnetic wave. On this slide here, we have a demonstration of 3 different types of polarized waves. All the way on the left, we see that all the vibration takes place in a plane that's tilted at a certain angle. In the center, we have a vibration of light where the vector of vibration is basically moving along the circle, so we're talking about circular polarization. And finally, on the right hand side, we see that vibration is occurring along the elliptical shape, so we're talking about so-called elliptical polarization. Circular and elliptical polarization can also be defined as either left hand or right hand based on whether the vibration occurs counter clockwise or clockwise. while the linear polarization can be either horizontal or vertical based on the plane in which the vibration takes place. We can adjust polarization of light by using so-called polarizers. Polarizers is basically a plastic sheet that is made out of material that contains certain type of crystals that would affect the polarization of light that is propagating through that type of a material. So what basically is taking place as the light propagates through this type of a polarizer is that the crystals would be absorbing a specific component of in a specific component of the light, and would transmit other component of a light. So after passing through linear polarizers, or unpolarized light would be emerging as a linearly polarized light in this case, like as shown on this slide, in a vertical direction. So what you have in front of the polarizer is unpolarized light that's represented by all these different arrows. In other words, the light vibrates in all possible directions. So we're talking about unpolarized light. It turns out that unpolarized light can be represented by two components, the horizontal component and the vertical component. And if a horizontal and vertical component are passing through this filter, it turns out that all horizontal component contribution is going to be blocked by the filter, while the only component that's going to be passed over on the other side is going to be a vertical component. So what we have over on the other side is a vertically polarized light. This is a concept that has found many applications, many real-time applications. Specifically, sunglasses, polarized sunglasses are one specific application where linearly polarized materials are being used. So unpolarized light that's coming from the sun is going through the effect of polarization, where over on the other side the light is significantly reduced as only one polarized component is being passed through, and as a cumulative effect is the light that's coming through our eyes is significantly reduced. So we are getting this darkened effect of environment that surrounds us.